Today we're going to be in chapter 2, section 1. We're going to talk about relations and functions. Not a whole lot of writing to do with this, but some things that are going to be pretty key as we move along in Algebra 2. So kind of up until this point in dealing with this, you've dealt with domain and range. And so now we're going to see kind of how that plays in and can make us tell the difference and help us determine relations and functions and move along. So something that I would probably write down is this box, this key concept box found on page 61. And here's what it's saying. We can have different types of functions. So numbers have relations. You can have numbers that go together. But when we get specific now and they fit a certain pattern, it can become a function. All right. And so as we look at functions now, we have stuff that goes on. So I'm just going to look here at this key concept. We have something that's called a one-to-one function. Right? And when we're dealing with a one-to-one function and we look at the domain and we look at the range, a one-to-one function, all right, is going to have the elements of the domain. So each one of these numbers, in this instance, I'm just right here in this box. Let's say those numbers are 1, 2, and 3, and we've got this range of D, B, C, and A. This is just a mapping. 1's going to the D, 2's going to B, and 3's going to A. If that's how this was set up, this would be one-to-one, because the domain pairs with exactly one unique element in the range. So 1 goes to D, 2 goes to B, 3 goes to A. Those are all unique that it's going to. The X's don't repeat. Not more than one X goes to a different letter. Okay, each X is married to a different range value. That's how we learned it earlier on this year. All right, so this would be considered a one-to-one function. Each X has a unique Y value. All right, the next thing that we have is we have something called onto. All right, so let's look at this next box. In this, they give us the domain as 1, 2, 3, and 4. And again, those are typically our X values. All right, and they give us the range as just D, B, and C. All right, and 1's going to D like it was in the last one. 2's going to B, so those are the same. We have some change-ups here. 3 goes to C, and 4 goes to C. Okay? So what onto is each element of the range corresponds to an element in the domain, or all the ranges are used. This makes an onto function, okay? You're like, well, I don't understand. Well, look back at the first one. See how in the range we had this element C that wasn't used? So this is not onto. This one is onto, all right, because each range was used or corresponded with an element of the domain. Now, this is not one-to-one because these X's go to the same Y. 3 and 4 are married to the same value, that value being C. All right, that's what keeps this one from being a one-to-one function. So there's the difference. Now, very simply, the other thing you can have is you can have both. And when I say both, I mean both one-to-one, all right, and onto. And very simply here, you can see the drawing again on page 61. The domain is 1, 2, 3, 4. Our range is D, B, C, A. And they're just drawing them straight across, which is fine. But each X has its own Y, has a unique Y, and all of the Y's or all of the ranges are used. This is an example of both one-to-one and onto. So one-to-one is that each X has its own Y, all right, and it's not married to the same Y, or those X's aren't repeated. Onto, all the range values are used, and then we have both. All right, so let's go just jump down to example 1 down here. Now I'm going to go ahead and tell you, I like doing this as a mapping. I think it's easy to see that way. I will leave that up to you, so you can just leave it as ordered pair, or you can go right out the domain and range. I like to do it as a mapping. So here we go. We're going to find out, all right, the domain and range. We're going to determine if it's a function. If it's a function, we're going to determine if it's one-to-one, onto, both, or neither. Now, we didn't go over any neithers, but obviously a neither would be where the X's don't have a unique Y and all the range values aren't used. So be careful when you run into that. I'm going to jump down. They've already split up my domain, so I'm going to write it. -6, -5, -3, -1, 6. I would say proper etiquette there is to write them in order from smallest to biggest. Remember, the -6 is the smallest number in this column. All right, do my range over here. -9, -7, -1, 7. Coach, where'd you get those? We got those from the ordered pair. Okay, let's go tag them up and see. All right, -6 is pointing at -1. -5 is going to -9. -3 is going to -7, sorry. -1 is going to 7, and 6 is going to -9. Now, if you learned anything about the last one, you saw that when I had two different x values go to the same y, that it wasn't 1 to 1. Each x doesn't have a unique y. So this is not 1 to 1. Now, this is a function. So when we did this a few weeks ago when we were talking in chapter 1 about functions and relations, this is a function. All right, each x has its own y. All right, each x has its own y. Now, I have to determine what type of function. Is it 1 to 1, on 2, or both? We just hit, hey, these two x's are going to the same y, so it's not 1 to 1. Each x doesn't have its own y, right? But every element of the range is used. Everything that we wrote down in the range has an arrow going to it, so this definitely means that it's onto. So our answer here would be, hey, it is a function and it's onto, all right? If you have this chart, this key concept chart written down, I think that that's something that's going to help you quite a bit, all right? Let's go on. That was example 1. That was part A. Let's look at part B. See if it gives us a little bit better picture right here, okay? So again, it gives us a table this time. I'm going to go ahead and do my domain and range the same way, all right? So my domain here, remember, we're not going to repeat. So 2's happening twice for my x's or for the domain. I'm not going to write that twice. My smallest domain value is -2. My next one's -1. My next one's 2. So I'm using 3 domain values, right? My range goes -2, -1, 0, 1, and 2. All right, we've got all 5 range values. Now let's see what we got. All right, so looking again at the ordered pair. 2 goes to -2. -1 goes to -1. -2 goes to 0. -1 goes to +1. All right, so right now we know, all right, that this is not onto. Now, we don't even know it's a function yet, but based on what we've seen, we're kind of sorting through all that in our head. And the last one is 2 goes to 2. All right, so again here, each x went to its own y. But look at -1 right here. It goes to -1 and to 1. That's saying, hey, -1 is married to 2 different values. This is not even a function, and we're done. It can't be 1 to 1 or onto if it's not even a function. So there's an example of that. All right, let's keep going. Discrete and continuous relations. That's pretty simple. Discrete is just ordered pair, all right, that don't have a line through them. So if it's a scatter plot where there's points all around, or if it's just points, we call that discrete. If we draw the line and that line is continuous or keeps going in both directions forever and there's no breaks in the graph, that's how we call it continuous, all right? So I'm going to teach you a thing, how from a graph, if you can tell if you have a function or not. That's this thing called the vertical line test, okay? So look down here at the bottom of page 62. So to pass the vertical line test, what that is representing is, like your pen or your pencil is an x value. And so if your x value touches the graph at 2 places or more, then that x is married to 2 or more y's, and that means that it's not a function because each x has to be married to a unique y for it to be a function. Now, you can kind of see the dotted line here. If you can imagine that dotted line being or going back and forth across this, or if my pen is that dotted line, this pen never touches my parabola more than once anywhere. As I drag it vertically, kind of looking at the front side of the pen right here, you can see there's just one spot that the pen touches the graph. Again, a nice visual here would be just imagine that dotted line going back and forth. It would never intersect this parabola more than once. So this is a function. Now, if this graph was flipped on its side, look at this dotted line. This is a great example of not a function. See right here where this dotted line is touching the graph or that solid line twice? So what we're saying is, hey, x is 1 right here, but it's married to -2, and up there in between 1 and 2, it's got 2 different y values. Each x has to have a unique y for it to be a function, so this one is not a function. This would be something that would be great to copy in your notes right here, this key concept, all right? I'm not going to write it in mine, but you write it in yours. All right, let's go to the top of the next page, page 63. It says this graph shows the length of the Tour de France in kilometers each year from 2000 to 2013. Is the relation discrete or continuous, and does it represent a function? So there's really nothing to write here. If I look and it's just a bunch of dots, there's not a continuous graph drawn. This is a discrete graph. That makes sense. Each year is its own point. We're not talking about every day in between the year. We're just talking about each year of the race, all right? So this is a discrete graph. Now, when we have to talk about if it's a function or not, I've got to see, and if I can do the vertical line test, does each dot touch my pen only once, or as I hold it vertically, is there a spot where two dots touch the pen? Because if there is, then I'm going to have a representation that's not a function. But look, every time I drag my pen vertically, there's just one dot at a time. I'm watching the right side of my pen or the front side. Now these two are close, but again, they're not on the same X line. That's what my pen represents, so we're good. We're good there. Only one dot touching my pen. Only one dot, only one dot, only one dot. So this would represent a function, and then we could go draw it up and try to figure it out if it was one-to-one or on-to or both, but they didn't ask us to do that. That's something that we could do. All right, now we're going to talk about graphing relations. I'm going to be real honest with you. When we start graphing, whether we get into linears or quadratics or whatever it is, this is something that we're going to do in the calculator, okay? So if I have, like this is linear, y equals 1/2 x minus 3. They graphed this up. They made a table. These aren't the only points on that line, but they put those points and they draw the line. All right, then it says, hey, is this thing one-to-one, on-to, both, neither, etc., and then state whether it's discrete or continuous. Obviously, it's continuous. That line goes on forever. So if you want to go on y equals in the calculator, you can do that. I'll show you in class with this assignment a website called Desmos to show you how you can draw that in there and get the same thing. All right, so basically for it to be one-to-one, each x, all right, has to go to a unique y, which they do, even the ones they pick. But any x that you pick on this line is going to have its own y. So it is one-to-one, all right? And then each y has got to be used. Well, if we have this graph, if a graph's made up of points, then each y is used on that graph. So this would be both one-to-one and on-to. You're going to see a lot of the same type things even with the parabola here. You're going to use x's. So what we're saying mathematically is, can you plug in an x and get a y? Well, yeah, you can square an x, add 1 to it, and get a different y. Up here, you can multiply any x by 1/2 and subtract 3. You're going to get a number answer. There's nothing funky that's going to happen, all right? So these are going to be continuous because the graph keeps going. Again, when it's just a scatter plot, you're looking at discrete, all right? This is stuff that we should be pretty good at. Let me fly through this next bit, and we're going to be done. So what we're going to introduce you to is independent and dependent variables. Independent is your domain. Dependent is your range, or independent is the x, and dependent is the y. Now we're going to start plugging it into this deal called function notation, all right? Stuff that you've worked with a little bit about plugging in. I'm going to go through it real quick, and we'll be good. So here we go. Example 4 right here. It says this, f of x equals 2x squared minus 8. And then it says this, in A it says find f of 6. So this is function notation. All f of x means is y. So when we see f of x, that doesn't mean x, that means that's your y value. So when they give you this notation and say, hey, find the f of 6, this value right here is your x, and you're just going to go plug it into your equation, and you're going to solve it. So it's really going to look like this. So if I had 2x squared minus 8, I'm going to take that 6, and I'm going to plug it in or substitute it in for that x. We're flip-flopping them out. So that becomes this, 2 times 6 squared minus 8. Now that's something that's pretty easy to do in a calculator. Let's go through order of operations as a good review right here, okay? So yeah, I put parentheses, but there's no math going on in there. That's just a 6, but I do have an exponent. So my first step will be to do 6 squared. 6 squared is 36, so I've got 2 times 36 and minus 8. Now PEMDAS says, hey, multiply these before you subtract. So 2 times 36 is 72. I've still got the minus 8 going on. The last step is to subtract. 72 minus 8 is 64. There you go. So when you plug in 6 into this equation, you get 64. Now what's important to understand, and where we're going to go, is you just found an ordered pair on this graph. This 2x squared minus 8 graph contains the point 6, comma 64. Now we're not going to graph that right now. That's something that's nice to know. Now it gets a little bit tricky. Look at example 4, part B. It says this, find the f of 2y. So here's what it means. Go to your f equation that they gave you, which is still the same one. We're still in example 4. But everywhere I see an x, I'm going to plug a 2y. So this is going to become my x value. You're like, Coach Lane, that's weird. Yeah, it's a little bit weird, but it's stuff that we've got to be able to work with. So again, I'm subbing this value in for x. You said, well, f of x was y. I'm telling you the stuff in the parentheses, this is f of x. Go sub in what they tell you. So it's going to look like this. 2 times 2y, and that's squared minus 8. I just subbed in 2y for x. You can see the flip. It's kind of here. They're talking about x here. So here I'm going to sub it out. All right? Now follow order of operations again. I need to square this. So I've got 2 times. Now 2 squared is 4, and y squared is y squared minus 8. Everybody see that? Catch on to that. We'll go over exponent rules later, but I just square the 2 and I square the y. Now I multiply. 2 times 4 is 8, and I've still got the y squared attached, and then I've got minus 8. Well, now here's the deal. I don't have any further to go. I don't know what y is. I can't plug it in. So this is my value in this equation for y. And you're like, man, that's weird, but here's what the ordered pair would be. Okay? My x value was 2y, and my y value, because of that input right there, became 8y squared minus 8. If we were ever given the y value in this problem, I could go find an ordered pair on this graph following that little formula right there. Okay? Don't make that harder than it is. It's stuff that you can do, and it's stuff that you can be successful at. But now you have a really good example of that too. All right? We're going to keep on. We're rolling in to start chapter 2. Make sure you're getting everything written down that I write down, and then you're always welcome to go back in and add some of those key concepts or anything like that from the book that you see. Thanks.